Hello class, this is a video tutorial on modeling exponential growth. Exponential growth is observed mainly in nature, and it's seen mostly in the growth of population. It follows the following equation: y equals p times a to the power of x. Y is the population at time x. P is the initial population size. A is the multiplying factor. It's also known as the rate of growth. And X is time. Time can be measured in hours, days, months, etc. And I'll give you two examples of what we mean here. So we have bacteria population. Notice how instead of Y we have B for bacteria. The initial population size of the bacteria is 100. It'll be 100 colonies or whatever it might be. The multiplying factor or the growth rate is times 1.25 per hour, because the measurement that we're doing, T, right, is in hours. Here's another example: the number of cases of infected with flu over 3 months. We have I for number of infected instead of Y. T is we're measuring in days. The initial population size here is 150. And the growth rate is only 1.07, which means there's 7% more per day than the previous day. So let's get to a numerical example here. A fish population is estimated using the formula. Here we are. Where N is the number of fish and T is measured in years. Graph the fish population between 0 and 5 years. So for this, we're going to need a calculator. Let's work alongside here. For this, we're going to be typing in this following. Let's write that in first. So 500. For this, I'm just going to use brackets, meaning times. And this power here that goes on top, okay, that's what we're going to be substituting as we go along. So to the power of 0, well, that's 500. If we do 500 times 1.5 to the power of 1, well, that gives us 750. If we do the same thing, 500 times 1.5 to the power of 2 is 1,125. And this continues like so. In the event that we get a decimal place, because we are measuring a fish population, it's impossible to get half a fish and consider it alive. So in this case, we're going to round up or down to the nearest whole. In this case, we're going to round up to the nearest whole number. So let's move right along. So 500 times 1.5 to the power of 4. This will give me 2, 5, 3, 1, rounding down to the nearest whole. And lastly, 500 times 1.5 to the power of 5. And one more time, we're going to round up. 3797. And that's our table of values. Now from this, we're going to plot our points onto a Cartesian plane. I have one here prepared. So at 0 years, so T is here, T is along here. At 0 years, we have 500 fish. At 1 year, so let's draw this. At 1 year, there are 750 fish. So we're going to go to 750 and go across. And where those two lines meet, that's where we're going to draw the dot. At 2 years, 1125. So approximating here, this is 1,250. Half of that, halfway between that is about here. So it would be 1125 is here, which is exactly what we want. So 1125 would be approximately here. Drawing the dot and erasing my lines. At 3 years is 1688. So let's go along the bottom for 3 years. At 3 years, we want 1688. So this is 1750, but we want 1688. That would be about, say here. There we are. Now this doesn't need to be entirely accurate because it's impossible for us to manually draw this many points. So at 4 years we have 2531. So at 4 years, 2531. 2500's here. Let's make it very slightly above that. Extending that line. There we go. So where this point meets, is where we draw our dot. And lastly, at 5 years, here at 5 years, is 3,797. So 3,700. That's 3,750. So let's put it slightly above that. There we go. That is our point there. Joining all these dots together. Remember, this has to be as smooth as we can in a curved line. So it shouldn't be a straight line like this. You should try and curve it very slightly along the way. Okay, so let's do this. Oops. And onwards. Hope we can see what it's kind of looking like. There's a general trend where as the population gets bigger, it's getting steeper as we go along. I've actually prepared one earlier. As you can see, we got pretty close. This one here was drawn on a graphical calculator, so this is 100% accurate. So let's utilize this graph that we've got to model and predict the values that we have here. How many fish were present after 2 years? Well, from this, it's actually very simple. We can do it one of two ways. Okay, let's do this graphically. Using the graph, it's telling us it's about at this point here. Okay, and that point is about, it's halfway between 1,000 and 1,250. Halfway between that is actually 1,125. Or because we have the graph here, we have the equation here, we can just use this. We can just use this and substitute the value of 2 into here. But we've already done that. It's there, 1,125. So using the equation, we get the same thing, 1,125. Same deal, if we use the graph for 3 years, it would give us this number here, which is, at this point, we would, or I would, approximate it to be, well, from the looks of that, I'm getting halfway between 1,500 and 1,750. Halfway between there is 1,625. So using the graph, I'm getting 1,625. But according to the equation, if we substitute t equals 3 years into this equation, so we get 500 times 1.5 to the power of 3, 1,687.5 exactly. 18 months. Okay, so before we continue, we have to be careful because 18 months is actually, if we do 18 divided by 12, that's 1.5 years. So 18 months is equal to 1.5 years. So 1.5 would be about here. And at that point, according, whoops, let me draw that again. According to the graph that we've drawn, that will give me, well, 750 is here. So from the looks of it, that's 875. So according to the graph, we're getting 875. But if we substitute 1.5 into the equation, so let's substitute that in. 500 times 1.5 times 1 to the power of 1.5. That's giving me exactly 918.55, which is approximately 919. So now the point that I'd like for you guys to learn here is that depending on how accurate your graph is, okay, it's fine to just utilize the graph if that's all you've been given. However, if we've been given an an equation, it's best to use that over the graph. But approximating from the graph is just fine. Let's do one more question. How many extra fish will be present after 4 years compared to 2 years? So now a lot of people assume we just take a look at 4 years. So 4 years is this, and we compare it to the 2 years, and we find the difference between the two. However, if you read the question, how many extra fish will be present after 4 years compared to from 2 years? So we're just going to take these two and we're going to subtract them, because this is the 4th year compared to the 2 years. So 2531. So 4th year, 2531. 2nd year is 1125. We're going to subtract the two from each other. I'm just using my calculator here. 2531 minus 1125. The difference is, so minusing these two, is 1406 difference. Okay, so I hope that gave you an insight into using, well, first to completing a table of values from a exponential growth, plotting them and graphing them on a Cartesian plane, and using the graph and the equation to determine points and do some extra calculations between them in this question here. Hope to see you in the next video. Best of luck.